Last Tuesday we were talking about the morphology of semi-crystalline polymers. We talked about a technique known as differential scanning colorimetry. And I said a little bit about some polymers that we're particularly interested in here at Manchester, which are interesting because we've taken away their flexibility, their ability to reorganize themselves. And that gives rise to some useful properties. So in the first 2 weeks we've talked about polymers, we've introduced the concept of polymers, we've talked about the physical states in which we commonly encounter. We've talked about glassy polymers, rubbery polymers, and semi-crystalline polymers. So now for the next 2 weeks, we're going to turn to another topic, which is really one of the most important questions we might ask about a polymer, because what we know is that polymers are big molecules, and so one of the most important questions is just how big are they? How can we work out how big they are? And of course, we're going to find a complication is that actually we're dealing with mixtures. And so how do we account for the fact that we very, very rarely have a single sized molecule in a sample? We have a mixture of different sizes. So that's the sort of thing we're going to talk about today and tomorrow, and next week we're going to focus on a couple of experimental techniques that give us at least some of the information that we're looking for about polymers. Hi there, make sure you've got a handout. So, now if those of you who are in your 4th year, you may have met some of this material before if you did Chem 20710 in your 2nd year. Which means if I ask some questions, there should be some people here who've got the answers, just like that. So we don't, you don't need to be quiet and silent. We can all come up with the answers. I can see someone there who I know is in the 4th year and I know has done this before. And anyone else, if you need some help, go to the 4th years. This is the last time, I think, that 4th years and 3rd years will be in the same class, because that whole structure is changing after this. Okay, but let's just ask a basic question. Okay, we've got some polymers, they're big molecules. First of all, how are we going to describe the size? Are we going to sort of talk about how long a chain it is, that it's a chain? Or if it's a coil, how do we take account of the fact that it might be more or less expanded? So, what different ways can we think of to describe how big a molecule like this might be? So let's have some ideas. We know that some people have got some ideas straight on. So, what physical quantities might we use as measures of the size of a polymer molecule? How might we describe the size of a polymer molecule, given what we know about polymers?
Molar mass.
Say again, molar mass. That's a good one. We're going to talk a lot about molar mass. We'll come back to that a bit later. But how else? That's not the only way to describe the size of a molecule. How else might we talk about it? Viscosity is something which relates to size, and we're going to see that next week. But what type of size does it relate to? Sorry?
The length of the chain.
The length of the chain is... So we can talk about how long a chain is, and we can talk about that in different ways. We can say, suppose we stretch a chain right out, how long is it? But of course, we never meet a fully stretched out chain. In solution or in the rubber, we know it tends to coil up. And even when it crystallizes, we now know, we don't usually get fully stretched out molecules. They tend to fold backwards and forwards. But if we think about a polymer in a rubbery state or in solution, we actually have a coil. Okay, and so we can think about a number of things. We can think in terms of what sort of volume does that coil occupy. But of course that coil is also going to contain a lot of solvent. So we have different ways of thinking about the volume. And one, which is important in viscometry, is what we call hydrodynamic volume, which we'll come back to in a moment. But you might also think, okay, we've got a coil. It can be a very compact coil, it can be a very expanded coil. How can we describe that? One way, which you're not going to meet too much on this course, but you will if you do a more advanced course, is in terms of the end-to-end distance. So it may not be fully stretched out, but we can still think in terms of how far the ends are apart on average. And that's important because when we do chain statistics, which you'll be pleased to know you're not going to do on this course, that gives some very nice, straightforward, easy equations. But there are other things as well. Let's just have a look at a few of the possibilities. Just think about how else might we describe it just as a chemist. You know, we're putting monomers together to make a polymer. So what might be a very simple description of the size of the polymer?
Number of units.
Mass. We've got mass. We've already mentioned mass. Anything else?
The number of repeat units.
The number of repeat units. That's a good one. More repeat units, the bigger it is. That's a useful one. Okay, so let's think about something. So actually, let's start there, because when you go on to think about polymerization and start thinking about how we talk about how the polymerization kinetics affects the product you get, then you usually start by thinking in terms of, on average, how many repeat units do you end up with in the chain? And that's often called the degree of polymerization. Degree of polymerization in this context is not the same as extent of reaction. Don't get confused. You often will. Some of you in an exam will get confused. Degree of polymerization is how many repeat units are there in the polymer chain. And sometimes it's symbolized by dP. Sometimes that's called the chain length. In some books, symbolized by an X. But in each case, this is just a number. How many repeat units are there in the chain when we finish? So that's one way of describing the size of a polymer molecule. Of course, what we can do is say, right, imagine we stretched out our chain. We never see it like that, but even so, imagine we stretch it out. Then how far is it in nanometers or whatever from one end to the other? Actually, sometimes it's useful to think about that, even though we never encounter it. And that's what's known as the extended chain length. And that will have units, because it is a physical length. Whereas the chain length, when it means degree of polymerization, is just a number. How many repeat units are there in that chain? So that's a couple of ways of describing the size of a polymer molecule. Here's another one which I just mentioned. If we have a coil, we might just focus on how far are the ends apart. And as I say, that's actually a useful one when one looks at the statistics of how chains behave and tries to develop a theory, for example, of rubber elasticity. Another one which, again, you're not going to meet on this course, but becomes important if you do a more advanced course, is the radius of gyration. That's important in light scattering studies, for example, which we'll only just very briefly mention on this course. But if you imagine our chain is made up of lots of little segments, and each segment has a certain mass, and if we work out the distance from each segment to the centre of gravity, so for each segment there's a different difference, R1, 2, 3, 4, whatever, we take the mass and multiply by the square of the difference, add that up over all the segments, divide by the total mass, we have the square of a radius of gyration, which is a useful measure of size. And it's something that can be determined by certain experimental techniques. So we've talked about a number of ways of describing polymer molecules in terms of how many repeat units are in the chain, how long is the chain if we stretch it out, what is the end-to-end distance when it's a coil, or the radius of gyration when it's a coil. I also mentioned earlier this thing called hydrodynamic size, which we describe in terms of an effective radius or effective volume. And the problem we have here is if we've got a polymer coil in solution, for example, then we don't just have polymer, we've got lots of solvent molecules. And depending on the solvent, it actually might be quite a sort of a big coil or quite a small coil. So we've got to take account of actually the size of the coil, even for the same sized molecules, because that will affect things like viscometry, how viscous is the solution. That depends not only on the actual sizes of the molecules, but also on the nature of the solvent, how good the solvent is at making the coil expand or contract. But what we do very often now as scientists, we've got used to the idea that we always start with a simple model. We only make it more complicated when we have to. So if we think about ideal gases, we start with the ideal gas model, which ignores the size of molecules and ignores intermolecular forces. We only make it more complicated when we have to. And the simplest model of a polymer coil is just to imagine it's a solid sphere. That's a reasonable approximation sometimes, not other times, but it's a good start. And so, from the point of view of at least of certain types of experiment, we can describe the behavior of a polymer coil in terms of an equivalent solid sphere. Now, the solid sphere will have a much smaller radius than the radius of space that actually contains polymer, because the polymer coil is expanded, it's swollen by solvent. But nevertheless, from some points of view, as a first approximation, that's it gives us some ideas of what happens. So when we think about the effective hard sphere that a polymer coil behaves as, the radius of that sphere is the hydrodynamic radius, the volume of that sphere is the hydrodynamic volume. Now, why is that useful? Well, actually, we're going to see next week it's really useful when we talk about gel permeation chromatography and dilute solution viscometry, because they actually depend on the hydrodynamic volume or the hydrodynamic radius. Hydrodynamic is about how things interact with a fluid in flow. So hydrodynamics refers to all those techniques which involve fluids flowing and how they're affected by the presence of a solute. Viscosity, diffusion, sedimentation, behavior in a GPC column, in a liquid chromatography column, liquid flowing fluid, all relate to hydrodynamics. And then, of course, there's the one we should all be familiar with, the molar mass. Now, here's something we really have to watch out for. Does molar mass have units? Well, molar mass does. Molecular weight doesn't. So if we say molar mass, then it's a mass, so it's grams per mole. So the normal units we encounter, normal units we use in chemistry are grams per mole. But of course, this actually gives rise to a problem, because if we're using SI units, now what's the base unit of mass in the SI system? Kilogram. Yeah. Okay? So if you want to do a calculation using SI units, then you need your molar mass in kilograms per mole, because the base unit in the SI system is the kilogram. But we normally have molar masses in grams per mole. So that's something to watch out for. If you're doing calculations, where you have to calculate a molar mass, again, we're not going to go into that too much in this course, but if you do a more advanced course, it will become really, really important. If you're using SI units, you'll get your molar mass in kilograms per mole. And that can really confuse people, because they get an answer of 200 and you think, that's not a very big polymer. But it's 200,000 grams per mole. And this emphasizes something you should already know: units matter. And in exams, the most common mistakes in questions that involve calculations have to do with units. Always be aware, if you're dealing with a physical quantity that should have units, what those units are, and that you're using them appropriately. Of course, the unit gram per mole, of course, is not a name. Chemists don't tend to use it very much. Life scientists do a lot. Have you all come across the term Dalton for that unit? So a gram per mole is a Dalton. Perhaps we should use it more, because of course John Dalton, he spent his life in Manchester, most of his life in Manchester. Born in Eaglesfield in Cumbria, but spent most of his working life in Manchester. Perhaps you ought to use his name a bit more. But you'll also come across the term molecular weight, which is actually strictly relative molecular mass. So it's actually dimensionless. It has it's the same number that you have if you quote a molar mass in grams per mole. But not all books follow that convention. So you will find some books which give units to molecular weight and some books which don't. You just have to be aware of these differences. So we've talked about a number of different ways which we can describe the sizes of polymer molecules. Molar mass is just one of them. And actually, as we'll see next week, although we might set out to determine the molar mass, we may actually measure something else that has to be related to a molar mass. But now, here we have our next problem. If we take a sample of a polymer, of course it doesn't matter, we've got 3 polymer samples here. These are all the same polymer. This is polyoxyethylene, gases. It's OCH2, CH2 in the backbone. And this is a low molar mass sample, 300 grams per mole. It's liquid. This one has a molar mass of 1500 grams per mole. It's now sort of a waxy solid. And this one has a molar mass of more than 5 million grams per mole. And you see it as a sort of a powdery stuff. You can't use this liquid for the same things as you would use this solid. The molar mass matters. It's one of the things we need to know about a polymer. It can be the same polymer, but the properties will depend on the molar mass. But not only on the molar mass, because if we have almost any sample of a polymer, we don't have molecules all the same size, we actually have mixtures. We'll have some little molecules and some big molecules. And so one of our most important questions is not just how big are the molecules, it's what sort of mixture have we got, which we express in terms of a distribution of molar mass or some other quantity. This is the thing that, one of the things that really upset the organic chemists. Do you remember I said that back in the 1920s, Hermann Staudinger was trying to convince people that polymers really were big molecules. And there was a lot of resistance from the academic community at the time. And I mentioned one reason for that resistance, which was that they got fixated on the idea that a molecule must always be smaller than its crystalline unit cell. Well, we've seen now, we've talked about semi-crystalline polymers, you can have a unit cell with a chain passing through it, so we have regularity on a very small scale, but the chain can be much, much, much bigger than the unit cell. But because they'd got that idea in their heads that, you know, if you know the unit cell, which you can do by X-ray diffraction studies, the molecules must be smaller than that. That's what they thought. It was wrong. It doesn't, they don't have to be. But they've got that fixed in their mind. But the other thing is that if you're an organic chemist and you're used to making small molecules, you rely on certain things to decide when you've got a good product. Now, what do you do in the lab? You take a melting point and you expect a simple, well-defined melting point. And if your melting point is low, you say, I've got the wrong thing, or it's impure. But we've already seen when we're dealing with polymers, things aren't as simple as that. Because even if the polymer crystallizes, the melting point actually depends on the morphology. It depends on the history of the sample. So it can be absolutely pure, but you still get different melting points. It's not as sharp as you get for a little molecule, it's quite broad, relatively speaking. So all of the things that they used to do to work out purity and whether you've really got something just don't work. You've got to approach things differently. And one of the basic ideas back in the 1920s about chemistry was, you define, if you had a pure substance, it had a well-defined molar mass, because it was a single molecule. They didn't know how to cope with the idea of molecules which could be chemically identical, but were, they're all the same polymer, but actually you had a mixture of different sizes. So it's difficult for people to get to grips with it. But it's really important. So we have to think not only about how, are we dealing with a low molecular weight polymer or a high molecular weight polymer, but also what is the distribution of molar mass? What kind of mixture have we got? Now, this then brings us to something else, which is really, really important. And which as chemists, we should all be totally familiar with, but for some reason, it seems to create a bit of a mental block and be a bit of a sticking point. But it doesn't need to be. So, if you go shopping, go to the supermarket, go to a big supermarket, if you're looking for pineapples, they're usually sold singly. You have a price per pineapple. If you're looking for bananas, actually if you go to some of the small Tesco Expresses and things these days, they actually charge per banana. But in the bigger supermarkets, how do they normally charge for bananas?
In bunches.
Hmm?
Yeah, in bunches.
They come in bunches, and how are they priced? Per kilogram, by weight. Yeah. So we're quite used to the idea that we can go into a supermarket and we will encounter in the same place different ways of describing amount of something. We can count how many we've got, or you can weigh out how much we've got. Yeah? That's not a difficult concept, isn't it? There are different ways of describing amount. We can describe amount in terms of numbers, how many of something have we got. We can describe it in terms of amount by mass. What weight have we got? And we do it every day. Everyone is quite happy with going to the shop and they can buy one pineapple and half a kilo of bananas or whatever. We're quite used to it. And as chemists we should be used to it because all of the time, one of the most basic things, you can't do any chemistry without converting between things that have to do with numbers of things, numbers of molecules, moles of molecules, and things that we can actually measure out more easily, which is often weights. Yeah? So conversion between moles and masses, masses and moles, they're things we should be familiar with all of the time. Yeah? We should all be good at it by now. So there's nothing new with the idea that we can describe amount in different ways. We can describe it in terms of numbers, or we can describe it in terms of weights or masses. And that means when we describe the distribution of sizes or molar masses that we have of a polymer, there are different ways of describing the distribution depending on whether we're thinking in terms of numbers or anything to do with numbers, how many molecules we've got, how many moles of molecules we've got, what the molarity is, what the molality is, or whether we're thinking in terms of masses or weight, what weight of polymer we've got, or concentration in terms of mass per unit volume, or something like that. So we can divide our ways of thinking about amount of stuff in terms of whether we're thinking in terms of numbers of molecules or numbers of moles, or whether we're thinking in terms of mass of molecules that are present. And depending on how we think, we're going to see different pictures to describe the same thing. Now, of course, we can always convert between one thing and another. If we have a certain number of molecules of a certain molar mass, so if the number, and so if we indicate sort of one out of many possibilities by I, so I can be 1, 2, 3, 4, for all the possibilities that are present in a mixture. So if we've got a whole range of molar masses, M, 1, 2, 3, 4, but we're Mi in general, and we have a certain number of molecules, or number of moles of molecules of each of those molar masses, whether we're N, 1, 2, 3, 4, or Ni in general, we've just got to multiply the molar mass by the number of molecules, the number of moles, to get something that's a weight term, haven't we? Yeah? So Wi equals Ni, Mi. Or Ni equals Wi upon Mi. If we've got things in one way, and we know what the molar mass is, we can convert to the other. So let's see how this works for a very, very simple example. We're going to imagine we've got a mixture of molecules, and to make it simple, we've only got a small number of molecules, 15 molecules. Of course, a real polymer sample will have billions, but we're just going to think about 15. And we're going to make sure they're nice and small so we can see what's going on. So we've got a diagram here which is meant to indicate repeat units strung together in different lengths. So we've got some single repeat units here. Yeah, there we go. And we've got some dimers, we've got some trimers, and so on. I'm going to say the molar mass of one of these little circles is 100 grams per mole. So if we join two together, we'll assume nothing is eliminated, we've got 200 grams per mole and so on. So what we're going to do is we're going to plot the distribution for this sample in two different ways. As a number distribution and as a weight distribution. So first of all, we need to have a look at what we've got. Now the biggest molecule we've got there has got 5 repeat units. And there's no difficult math. If we've got 1 repeat unit, what did we say that the molar mass was? So if we've got 2 repeat units,
200.
we've got 3, 4, 5, okay? This is not, there's no difficult maths here, we can all do this, can't we? Right, now we're going to work out how many we've actually got in our diagram. How many of those single units can we see there?
4.
5? Are we all focused on 5? What about the dimers? How many dimers are there?
4.
4? So remember, now we're counting. Remember, this is a number thing. We're counting them.
Yeah.
Okay, how many trimers have we got?
3.
How many tetramers?
2.
And how many pentamers?
1.
Okay. It's easy, isn't it? Easy. Right. Okay. What mass of each species have we got present? So we've got 5 which have a molar mass of 100 grams per mole. So altogether, what mass have we got of that species?
500.
500. Actually, we'll come back to that in a moment, because actually we've got the information to plot the number distribution, and we'll come back and work out the masses. Let's just see what the number distribution looks like. So we plot, now we're going to plot something in the exam, we make sure we label the axes and things, so we need some numbers on the axes. So there we go, the numbers, we might go 0 to 6 in terms of the numbers, up to 600 or so in terms of the molar masses. So we can plot that data. We're going to plot it as a histogram because we've got discrete molar masses. So if we think of 100 grams per mole we had 5, 200 grams per mole we had 4, 300 grams per mole we had 3, 400 grams per mole we had 2, 500 grams per mole we had 1. So that's what our number distribution looks like as a histogram. Because we've got a lot of little molecules, as you go up in molar mass, you get less and less and less. Actually, that's broadly speaking what, that's a bit uniform, but broadly speaking, that's what a number distribution looks like for most polymers. You have a lot of little molecules, and as you get to higher molar mass, you have fewer and fewer. So this is a number distribution, because we're expressing in terms of number or something to do with numbers of molecules. Now let's go back to our table of data and think about the weights. Now, so we said that for the unimer, for a single unit there, we have 5 of them altogether. The mass of unimer is 500, whatever the units of mass are here, grams, if we've got a mole. The absolute amounts don't matter, it's the relative amounts that are important here. You can scale these in any way you like, as long as you scale everything by the same pattern. Okay, what about the dimers? We've got 4 dimers, each one weighs 200 grams per mole, so in the same units, what is the weight of that we've got present? 800. 800. Okay, not difficult math here. Right. And then the trimer, we've got 3. Each of 300 grams per mole, so
900.
And the tetramer,
800.
and the pentamer,
500.
okay. You can all see that things are starting to look different. We had a large number of small molecules, but what's it going to actually look like when we plot that? Now again, we need some numbers on our axes. Make sure we label the axes. In the exam, we'll lose marks if you plot some data and it's not properly labelled, because then it's meaningless. No one knows what you're plotting. And so now we've got, what do we have? 500, 800, 900, 800, 500. That is the weight distribution. So these are 2 different ways of representing the same mixture. If we represent it in terms of numbers, it looks different to what we have if we represent it in terms of weights. As one might expect. Because although we've got a large number of very small molecules, each one is small, it doesn't weigh very much. So it actually doesn't contribute to much to the total mass of polymer we have, as this one in the middle, where we've got sort of a reasonable number, but each of them is quite big. When we get up to here, we haven't got very many. We've only got 1. But because it's a massive molecule, it contributes just as much to the mass of polymer as all of those little tiny ones. So whether we are counting things or weighing things makes a difference in terms of what the shape of the distribution looks like. But these are different ways of representing the same distribution. You represent it as a number distribution or as a weight distribution. So if something's really small, you can have a lot of them, and they don't actually, and it can have a big impact on the number distribution, a tiny effect on the weight distribution. If something's really massive, you may only have one of them, it may hardly signify the number distribution, it can have a big effect on the weight distribution. So how you describe the distribution matters. In certain circumstances, the numbers might be important, in some circumstances, the weights. But they'll look different, but they're different ways of describing the same thing. Now, I said that it didn't matter, in terms of the shape of the distribution, it's the relative values of things that are important. Quite often, distributions will be normalized. So if you normalize by dividing through, for example, if you're thinking in terms of numbers, if you divide through by the total number, what you then have is a number fraction. That's you're normalizing it, so when you add up all the number fractions, they'll equal 1. Sometimes you might find a situation where you normalize for something else, so everything adds up to 100 or 1,000,000 or whatever's useful to you. But the number fraction, if you convert these to number fractions, and add up all the number fractions, it must equal 1. Similarly, if you take the weights, whatever they are, and divide by the total weight you got, then you're going to have weight fractions. And add up all the weight fractions, they'll equal 1. You've got to be a bit careful that you don't, however you scale one thing, you follow that through logically when you're converting between weights and numbers. But we can express things in terms of numbers or weights, number fractions, weight fractions, whatever's most appropriate. And of course, because we convert between weights and numbers, we can express our number fraction in terms of weights if we want to, but we need a molar mass in there. We can express our weights in terms of weight fraction in terms of number fractions if we want to, but we need a molar mass in there for the conversion. Now, when we did that very simple plot, we plotted the data as a histogram. We only had 5 different species. If we take a typical polymer sample, we're going to have tens of thousands, hundreds of thousands, millions of different species, depending on how big a polymer it is. So, although strictly any polymer distribution will be a discrete distribution, that means, what you'll have is you can have only certain molar masses. You can have only certain multiple of the repeat unit, plus or minus something for the end groups. Yeah, so you add another repeat unit, you actually increase the chain by a certain amount. And you can't have something in between those amounts. So strictly, a polymer distribution is always a discrete distribution. But because we have so many, we don't normally represent them as discrete distributions, as histograms like we did earlier. We normally represent them as continuous curves. They're not really continuous, but we've got so many options so close together, they're virtually continuous. So we can represent them as continuous curves, then we can treat things in terms of derivatives and integrals and such like, which some of you won't like, but which actually makes life a lot easier. So, supposing we've taken 2 distributions, and these are a bit like the ones we've seen. The number distribution starts big and gets smaller. The weight distribution goes to a maximum where we have a sort of a good balance between having a few very large molecules and a lot of very small molecules. That's very typical of the sorts of distributions you get for polymers. But now we're going to represent them, instead of as a series of vertical lines as a histogram, we're going to represent them as a continuous curve. These are meant to be continuous curves, so the resolution is poor on the computer plot of them. If we're thinking in terms of continuous curves, what are we plotting? On the x-axis we have molar mass. On the y-axis we have something which relates to a number or a weight, depending whether we're thinking about a number distribution or a weight distribution. In some books it's written like this. N with an N in brackets. The N in parentheses, those rounded brackets are parentheses, just tells us that this is a function of molar mass. We can also write, if we're thinking about a number function, it is dn by dn, where dn is the number of fraction of molecules with a molar mass in a certain range. So if we take our distribution, we imagine some molar mass m and think, right, let's take an infinitesimally small increase in m. So we've got m to m plus dm. Remember that little d means a tiny, 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 infinitesimally small increment in something. And we have a little tiny sliver, a slice out of the distribution, and the number fraction of molecules in that slice would be dn here. And it's an infinitesimally small slice, an infinitesimally small number. Similarly, if we're dealing with a weight distribution, we can write it as something which is a function of m, and dw then, in this case, would be the weight fraction of molecules in that little slice between m and m plus dm. So what does it, how do you think about this? What do those little shaded strips actually mean? So, if we're thinking about the number distribution, it's the area of that strip which represents dn, which represents the number fraction. Not the height, the area. And if we're working with number fractions, then the total area, if we integrate over the whole curve, then we end up with 1, because number fractions must add up to 1. If we have some other number term, then it will add up to something else. It will integrate to something else. Why is that important? Actually, it becomes important. You'll see why it's important next week when we say a little bit about how we analyze GPC data and what happens when you convert between different types of distribution. But when we're using these continuous distributions, first of all, what we're doing is we're saying, right, we've really got a discrete distribution, but we're going to represent it continuously, and therefore we can use derivatives and integrals to represent what's going on. So similarly with the weight distribution, the area of any little strip represents the weight fraction, if it's a weight fraction distribution, the weight in whatever term we're using that we have of molecules in that little increment of molar mass. And if it's weight fractions, then the total area must add up to 1. If there are those people who don't like derivatives and integrals, but by now you should, you're in your 3rd or 4th year, so it should all be fairly straightforward to you all. We're not going to pursue this very much on this course. We're just going to look at shapes and things. But you need to grasp the distinction between a discrete distribution and a continuous distribution. We're going to handle them slightly differently. And if you have an exam question and you're asked to plot a histogram, then plot a histogram. Don't plot a continuous curve. If you're asked to explain what a continuous curve represents, make sure you understand that. And I'm going to stop early today, get you thinking about that, but tomorrow we're going to come to the question, right, if we've got a mixture, not only do we have this problem that we've got to think how to describe that mixture in terms of numbers or weights, but if we measure any value of something, it's going to be an average. And so we're going to find we have different kinds of average that we have to think about.